Right, I got another graphing video for you where I'm going to try to show you 3 different kinds of graphs, the main 3 we use in physics: the acceleration time graph, the velocity time graph, and the distance time graph. All right, and we can use those graphs, those 3 different graphs, to graph the same event. So you're going to notice all my graphs are going to be 3 seconds. That's because it's the same event. Right, and we're going to look at 3 different events so that we can come up with 3 of the uniform accelerated motion equations. Now, what I mean when I say uniform accelerated motion is that our acceleration is going to be one number the whole problem. It's not going to be changing. Most of the time in this class, we won't have a changing acceleration, which is called jerk. We'll just have a constant acceleration. It'll be 9.8, or it'll be 0, or it'll be 5. So we're going to look at this situation where we have a velocity at the beginning of 6, and then we have an acceleration of 0. Okay, I've sketched the graph. Grab a different red marker, and it's a horizontal line at 0. The reason why it's a horizontal line at 0 is because the acceleration is 0. So for the entire graph, you should expect to be at 0. Right? Now I've drawn the corresponding velocity time graph for this. So it said I'm supposed to start at an initial velocity of 6 and then accelerate at 0. What does that mean? It means that every second, my acceleration is my meters per second. Every second I need to gain 0 meters per second. Okay, so if I'm at 6 and then I gain 0, I'm still at 6. And then I gain 0, still at 6. And then I gain 0, still at 6. Pretty simple. So if your acceleration is 0, you should expect your horizontal line on your velocity time graph. It's not going to be doing anything because you're not accelerating. Okay, so then we can look at the area that is underneath that velocity time graph curve. Right? Why would we look at the area? Well, because area is base times height. And if I look at those units, I got meters per second times seconds when I do base times height. Well, that's meters. So in other words, that area is going to give me a displacement, right? It's going to give me the length that I traveled from the starting point. And so if you have a positive velocity the whole time, you should expect a positive displacement. And we do here. So this area right here is what I want. And that area is really just like taking velocity times time. Well, when we have constant velocity like we do here, that shape's going to look like a rectangle, and we've already talked about the constant velocity equation, v times t, that's your displacement. Right, so 6 times 3, we get a displacement of 18. So at the end of the 3 seconds, we're going to be at 18 on my displacement time graph. Okay, and I've drawn a straight line from 0 to 18. It took me a few tries, but the reason I've got a straight line is because slope, whether this line is straight or how flat it is or how curved it is, the slope is the rise over the run. Right? Well, what's on my rise here? Distance. And what's on my run? Time. Right? So what is that? Well, it's speed, or if it's displacement over time, it's velocity. And so the velocity is the slope. All right, so what did the velocity do? Well, it was 6 all the time. So what's my slope doing? It's 6 all the time. That's a constant slope, something that all straight lines have. Right? So now I've changed the scenario slightly because I want to make a different point. Now I've swapped it around here. I've got an initial velocity of 0 and an acceleration of 6. So since my acceleration is 6, I'm going to draw a horizontal line at 6. And again, all of these acceleration time graphs will be just horizontal lines because the acceleration is going to stay the same magnitude through the whole problem. So I just stay at 6 for 3 seconds. All right, so now it gets a little more confusing to figure out my velocity time graph. Since this wasn't 0, I don't just stay at my initial velocity. So a good way to do this is to use the area under the acceleration time graph. Right? Why does that work? Well, when you look at an acceleration time graph, you have meters per second squared on one axis and seconds on the other axis. What do you get if you take meters per second squared times seconds? What's this rectangle's area units? Well, that's going to cancel with that, and you get just meters per second. All right, so in other words, the area of this rectangle is going to be your change in velocity. Right, so what is my change in velocity? 18. So I drew a line from 0 to 18 in the 3 seconds. Okay, you're probably wondering, how did you know to make it a straight line, not a curvy line? Well, oops, I made it a straight line. Come on, I'll get it yet. Made it a straight line because the slope of this is the change in velocity over the change in time. And that's acceleration. And since the slope is the acceleration, if my acceleration was constant, I need a constant slope here. And that's usually what's going to happen. Okay? So I wanted to give you another way to think about this 18 right there. Right? We have this acceleration equation which says that v final minus v initial over time is equal to acceleration. But another way that you can write that is v final equals v initial plus at, if you just manipulate it. Right? Well, in this problem, what was our v initial? 0. So v final really is just at. So I'm going to call this 18 number at. Now this is only true when the initial is 0. Okay, so now if I look at this area right here, this is another shape we know. It's a triangle, right? The area of a triangle is 1/2 base times height. So in other words, 1/2 t times at. Well, that's 1/2 at squared. Right, so the area of this is 1/2 at squared. And so 1/2 of the acceleration of 6 is 3 times 3 squared is 27. Right, 3 times 9 is 27. So I need to be at 27 at the 3 second point. Right, and notice that this is a increasing slope. Right, the slope is going to be my velocity, and my velocity is increasing. Slope needs to be increasing. Okay, I can't keep a constant slope because the velocity wasn't constant. So notice the progression here. You start with a horizontal acceleration graph, turns into a diagonal velocity graph, which turns into a curved displacement graph. Last scenario. I've got an acceleration of 2 this time. I have an initial velocity of 4. Right, so I draw a horizontal line at 2 for the 3 seconds. And now I want to find that area, so I can make my velocity time graph, right? So the area is 6. That represents my change in velocity. The change in velocity is 6 meters per second. So if I start with a v initial of 4, the final velocity is going to equal my v initial plus that area, at. Okay, so in other words, it's going to be 4 plus 6. So I need to end up at 10 at the 3 second point. Okay, and I could find the area under that as well. Okay, well, there's kind of 2 different ways to think about finding that area. One of them is to think of this as a trapezoid. Okay, it doesn't really look like a trapezoid that you would recognize. So you have to kind of get over here and look at it from the side and see it as having a side that's 10 and a side that's 4. Right, now if you remember, the trapezoid formula is you're going to average these two sides and then times it by the height. Okay, so what am I doing when I'm averaging this side and that side? I'm really taking V initial, that's the left side, plus V final, that's the right side, averaging them. So you just add them together, divide by 2, and then multiply by this, which is the time. Right, so that is one of our UAM equations for the displacement. Area under the curve is the displacement. So it's V initial plus V final over 2 times the time is going to equal the displacement. Right? There's a second way you can find this area, and that would be to think of it as a rectangle and a triangle. Okay? Well, we've already talked about how a rectangle like this just has an area of V initial t. Right? And the triangle, we've talked about having an area of 1/2 AT squared. So we could do displacement is equal to V initial t plus 1/2 AT squared. So let's check it both ways. So V initial is 4 times 3 is 12 plus 1/2 times A. Remember A was 2, so that 1/2 times A is just 1 times 3 squared is 9. Okay, so 12 and 9 is 21. We check it this way. We do 4 plus 10 over 2, 7 times 3, 21. So we should end up at 21. Okay? And again, because we had an increasing velocity, we have an increasing slope on our displacement time graph. Okay? So these equations really come from graphing. And what I want you to notice is to move from acceleration to velocity, find the area under the curve. To go from velocity to displacement, find the area under the curve. To go from displacement to velocity, look at the slope. To go from velocity to acceleration, look at the slope. Right, so that's how you move between these graphs. And you have to know things like your starting position, which in every graph we said was the origin, to make it simple. It isn't always. Your starting velocity, which here was 6, here was 0, here was 4. I have to specify that. And then the accelerations, which we had 0, 6, 2. So really there's 3 things to keep track of. They all have the same time intervals, but there's the position or the displacement, the velocity, and the acceleration.